It's gone.
Okay, so this is numerical method C3, and we are trying to look for where our function here has roots. So roots, solutions, same sort of thing. Basically, it's where the function passes through 0 on the x-axis, where the height of the graph is 0. So we're interested in that point there.
Okay.
So let's have a little look at what is actually happening on that graph at this point. So we're starting down here somewhere, and we pass through that line, and then we shoot off up there. We're going from negative height of the graph. It's not really a height, but you know what I mean, to a positive height of the graph. Below the x-axis to above the x-axis. So imagine we're going on a continuous line between -1 and 1. What is the only really significant value on our continuous line between -1 and 1?
We will go through 0, of course. We'll go through every value from -1 to 1.
Exactly, including 0. Yeah. So if our line is continuous, which on a curve like this it is, then if we're going from a negative number, say -1, through continuously to a positive number, we must pass through 0. So that means that when we're looking for values of 0, if we go from positive to negative, we must hit a value that would represent 0. So an x value that would give us a 0. And it doesn't matter which way around our graph is going. Again, we could be going from positive to negative in this case, but we're still going to go through that 0. So it doesn't matter what our graph is doing here. And in fact, this is what numerical methods is so useful for, because I don't know about you, but I certainly couldn't predict what that equation on the line is. Cubic, quartic, goodness knows what. I also don't think I have any tools at my disposal, even now, that would allow me to solve that value there, to find what that value of x is, unless I was using iteration. So when I don't have something like a linear graph or a quadratic that I know what to do with, I could factorize whatever, actually this is what's going to be most useful. But in this case, what we're looking for is a change of sign. So if we do find that case where we go from positive to negative or negative to positive, we know that in between those two values, we must have a root, a 0. So that's what we're looking for here. The question says show, so it's some kind of argument, some kind of proof, that the function, this is the function we've got a graph here conveniently, has a root between 1.1 and 1.6.
Okay.
So there's 1, so 1.1 is somewhere in here. And 2, 4, 6, so we're in there. That's the solution. In fact, we know that it's got that. So we know that we can just about see it there. At 1.1, our curve is below the 0 line, and at 1.6, our curve is above the 0 line. So, I mean, the graph really does help us here, because it tells us we're going to find that change of sign that we want to show that it has a root, that it has this equal to 0 thing. So, how can we know that this is negative, but how can we show that it's negative? What could we do? We know what the value of x is at the moment. We know it's 1.1 or 1.6.
So what we could do, we could substitute the value of 1.1 into the equation, right? And to find the value of y for one point, for one boundary, and for the other boundary for 1.6, right?
Yeah, brilliant. So if we can find that y value there, oh, that was terrible, but oh well, and that y value there,
it was.
It's really bad. Oh well, it's still negative and still positive. If we can find those values, then we know that it's going through 0, isn't it? I really are so bad. I'm so sorry.
So sorry. I'm helping with calculator, right?
It's okay. Well, we've done this before, so. Don't forget, everyone, that your e to the x button is above the ln, so you're going to need to shift.
Oh, thank you. I remember now. So, did I press?
I conveniently have worked them out before. This is one I did earlier. So when we've got the value of 1.1, so that's the value of x, don't forget. So we've just substituted that in where we saw x each time. That's given us minus 0.7958. And if we put in y equals, so x is 1.6 minus 6, then y is 2.153 and a whole more digits. Good. So we've now gotten the two values of y. One's positive, one's negative. we've got a continuous function running between those two values.
Absolutely.
So we've kind of shown the first part. We've given an explanation as to why the positive and we found the positive and the negative, but we need to conclude, don't we? Because we've got to show that.
Yeah, I think we can also write kind of explicitly, this is less than 0, this is more than 0.
Fantastic. Yeah, I definitely agree. So it is obvious, obviously, but treat your examiner like a bit of an idiot.
Okay. So, yeah.
Yeah, which is greater than 0. And so then we've got the change of sign.
Yeah.
We can see that we're going from positive to negative.
And the function is continuous. Yeah, I think that's also worth of mentioning.
Oh.
Yeah.
So we've got change of sign. Function is continuous.
I can write miss.
However many years of education, I still can't write. Change of sign, function is continuous. Therefore, we've got a root between 1.1 and 1.6.
Yeah.
Good. And that's it, isn't it? I mean, that's everything we need to do. So we've shown that quite explicitly. When we put in that value of 1.1, we got a negative y value. Put in the 1.6, we've got a positive y value. We've got a change of sign, a continuous function, therefore we must have a root. It must pass through 0 at some point between those two.
Yeah.
Brilliant.
I think we need,
Okay, so if we had a function like this, obviously it's a quadratic, so we could just use the quadratic formula, we could factorise whatever the formula is, but let's practice using this searching for a root, searching for this change of sign. And to do this, we use an iterative form. So what we want to do is to bounce forwards and backwards between two things to reach our destination. In the same way that we were looking at a positive and a negative, we almost want to consider all the positives and negatives as they approach a point.
What do you mean?
So, if we had, for instance, if we were trying to find this solution here, and we started at this point, we'd want to be able to kind of test all the points approaching in on it, so that as the negative values got larger and the positive values got smaller, we must have been zeroing in on an x. That's kind of where we're starting from, that kind of concept. And conveniently, because maths is so nice, we have a way of doing that without actually having to manually choose those points and pick in and narrow down on it. And that is an iterative form. So that's those kinds of things where you have x to the n plus 1 is 1 minus x to the n. So whatever our value of x to the n1, this was C1, so if you need to revise this, go back and have a look at this. What our value of x to the n was, take it away from 1, and that gives you the next value. So it kind of, the formula feeds itself.
Okay.
Yep. The way we get that to be able to use this iterative form is we force it to take the value where we just have an x on one side, so we get x equals, and then we have some other function. Okay. So we've got two x's to choose from here, so it's kind of just rearranging formula at this point. We can either use x squared or we can use that x.
Yeah, and it's a bit different to... Yeah.
Yeah.
A bit different to rearranging the formula.
It is, exactly. Yeah. So it's not rearranging the formula because we don't want to kind of factorise that out. We want to get x equals something, but we don't care what's on the other side. It probably will, well, in fact, it will contain other x's. It's also not the same as solving by factorising. So we can almost cancel through by an x. We don't care about that. We're not losing a function because we're doing this in a different way. So let's take the x, or the x squared.
X squared.
Take the x.
No, we'll take x.
Take x. Okay. So
take.
Yeah, let's take that x squared plus 1 is equal to 4x.
Yeah.
And then let's divide through by x.
Now I think we'll leave x squared on the left side, right?
Yep.
Take away 1 from each side, and then we'll divide.
Yeah, divide by x. Yep. So we've got x x is 4x over x, that's just x minus 1 over x. So we've now got it into this iterative form. We've got x equals, and then we've got some other function. Okay. So what we're trying to do here, this is our y equals x. This is y equals x here. This actually kind of ends up looking like we're trying to find these crossing points, doesn't it? Because we've got where x is equal to this other function. So we're looking where the function y equals x is equal to this function y equals 4 minus 1 over x. So to find this value of x, we're trying to find that point there. Yeah. And I suspect that point there, although finding that might be needing a different method. Okay. So if we set this up into iterative form, we need to set up x n plus 1 is equal to something of xn. So we've got 4 minus 1 over, here must be our xn. Okay, so that's our iterative form. Means whatever value we stick in here, we're going to then get a different value over here, and then it will feed itself back in again. Okay, so the question will often give you a starting point. It will say x0 is, in this case it's 3. So let's imagine it's here. We're going to find the value of y at this point, which is there. And then we're going to feed whatever that value in at whatever that value is, we're going to feed it in at that point as well. Yeah. Because this is y equals x. So what we're saying is, this is why we have x on this side. Because it means that whatever value of y we get, we can automatically feed it back into the equation. Yeah. Because y is x. Yeah. So whatever value of y we found, we're then saying, well, that is our x value. Yeah. So what we're saying is, okay, we're going to take 3, find out what the value of y is, and then feed that value of y as if it were a value of x. So if we feed the value of 3 in at x0, so then x1 will be 4 minus 1/3, which is 3 and 2/3, isn't it? Which is sort of 3.66666 recurring or something. So that's 3 and 2/3. Yeah. And then, because it's iterative, we're going to feed that exact formula, that exact number back into our equation. And then that line will give us that point there. Yeah. And then we're going to do the same thing again. We're going to feed that number back in, because it's y equals x, and find out what that one is. And this will, because it's math and because it's brilliant, converge on that point. So we're going to get increasingly close to whatever that crossing point is, which, because we've rearranged that formula, is actually that 0 value for that original equation, but at the moment is the intersecting point between those two lines. So we are going to converge on that point, which means we're going to get closer and closer and closer to it. Yep. So it's probably going to be a decimal. It's probably going to be something horrible, and you're going to start to notice that it's 3 point something, and it will eventually end up being 272, I think, and then it will start to.
How do we know when we should stop? Exactly. How do we know when we should stop to do iterations? Do you think?
Well, obviously, the more iterations you do, the more accurate you're going to be able to predict what that route is. Yeah. Normally, I think it will tell you what they want. So it will say to 2 decimal places to 3 significant figures. So I would overshoot it by a couple of decimal places. So do enough iterations so that, to say, if they want it to 2 decimal places, to 3 or 4 decimal places, you're getting the same answer consistently, and then round it. Because otherwise, who's to say that when you choose the 4th iteration and you get something and it's repeated, that the 5th iteration suddenly doesn't round it up or down to the next number? Yeah, so you want to overshoot by a little way, but obviously not enough that you're going on forever. Yeah. Yeah? Yes. So our whole point has been to find that 0. The way we've done that is to get this function x equals something. A, because we can set up this iterative formula. But the reason that iterative formula works is because that is now the comparison between that function y equals x and this new function y equals 4 minus 1 over x, and we're now looking for the intersecting points. Because all we've done is rearrange that formula. But that allows us to do this bouncing around thing, because y does actually equal x. So every value of y we get, we can change the same one for x. Our only other problem then is if sometimes there's going to be more than one way to rearrange something.
Yeah.
And in that case, normally your exam question will tell you to either take one of those routes by saying show that it rearranges to this particular way, or will guide you through taking both of them. But what will happen in this case is normally they'll produce two different routes.
Yeah.
So in the same way that on this previous graph here we had two different places that this would cross, rearranging this in two different ways would produce those 2 points.
Yeah.
So when we rearranged with an x squared, we were heading for this one, but if we rearranged so that we got a square root or something, we might have been heading for this second one down here. Yeah?
Yeah.
So in this case, we could rearrange this into two different ways and take you through it.
Mm-hmm.
Do we want to do that now? Should we do that as a separate video later?
Later.
Let's do it later. So work through the examples in the textbook. Make sure you've tried some questions and bring your questions and answers to class. Good luck.